Alright, so welcome to another one. So in this video, we do have now the data from the historical data from Y Finance and the macroeconomic data. We have pre-processed the data, cleaned it up, then we created features based on those data. I'm gonna show you how those data now looks like. Let me run the code first so I do know that the data is uh, perfect. So that is gonna run. Meanwhile, let's talk about what we're gonna be talking about in this video. So this video is gonna be creating baseline models before we dive into deep learning model. So we are gonna be creating ARIMA model and linear regression model. So why do I even need a baseline model at all? So before we dive into the deep learning model, we do need to understand that not every problem requires heavy computational model, deep learning model. If the model, if the data can get modeled with a simpler model, we might as well go with that. So we need to set a benchmark. So a simpler model that says is this is the minimum acceptable performance of a model. If the deep learning model performs lower than that, that means we do not need that deep learning model, or maybe we do need to tune that model, but the simpler model does a better job than a deep learning one, so we do not need that high computational model. But if the deep learning model performs better than this baseline acceptable performance, then we know that okay, the simple models cannot do the job with this data. We do need the deep learning models, but we might need to tune it a bit more to make it more better performance. So that is why we do need to create baseline performance models. So in this project, we are using a couple of those. One is ARIMA, which is used in traditionally with time series data, and the other one is linear regression. It's not ideal with time series, but it's a generic model that is a generic regression model. That's simpler parametric model, we can say. So I do believe the code has run. Let me show you. This is the historical data. That's how it looks like. It gives me the data from 1980s to today, March 26, 2025. And if I create the feature, clean this data up, and then if I model this data, let's see how it looks like. There you go. It gives me the data all the way from 1980s with this log returns and volatility, max drawdown, every other feature is calculated. I want to point out one thing though. I can see NaNs, which is non-existing, which is a null value basically. So that's why we need to apply the cleaning to this data frame. So I'm gonna apply that cleaning, and then we'll see if the data that we have is cleaned up. That means it fills out these null values or not. So let's do that. Okay, and let's now see the data if it has any null values. No, I don't see those NaN values there anymore. It has backfilled and forward filled the data and created a non-null clean data set for us. So that's how the data set looks like. Now let's jump onto the ARIMA model. The first type of baseline model that we're going to be doing, the ARIMA, is basically the classic baseline model that are used in whenever there is a time series type of data is involved. What ARIMA stands for is basically autoregressive integrated moving averages. So it's univariate time series model. That means, what do I mean by that? It means it only uses the past values of the target variable to predict the future values. Use the past data and based on that predict the future data. If I want to simplify it, let's break it down. ARIMA, A-R-I, and MA. So AR means number of lag observation that they are used for calculation of futures, right? I is basically degree of differencing to make the data stationary, and MA is basically the moving average term in how many past errors are considered, right? So in simple sentence, if I want to say I will predict tomorrow's return based on how return has moved over the, let's say, past 5 days, which is R. After removing the long-term trends, I want to remove long-term trends, which is I, and I will be correcting for the past prediction errors, that is MA. So that is a ARIMA model. It's a classic financial forecasting model. It's good at capturing the momentum and autocorrelation. We do have calculated the momentum, and it will do the autocorrelation between the features, and it's simple and interpretable and works well with the stationary time series. However, it's not always a bread and butter. There are limitations of a ARIMA model. It doesn't incorporate the external features. Remember, we are dealing with stock market data. It's not only dependent on the feature that we have and handy, right? It's not only dependent on, it is dependent on these macro indicators and the other features that we have calculated, like log returns and rule. But these are not the only ones that the stock market works on, right? If there is a news article that can affect the price of the stock more than this, right? And that news article that becomes natural language processing. You cannot simply quantify that into number. You can, but that's a very complex problem. For the sake of this project, the time series is, we have it the external features can affect it, right? So ARIMA has limitation with that, and it assumes a linear relationship, and the time series, a stationary time series. It works well with this stationary one. We do know that stock market is never linear. It's never okay. In long term, if you say, it might be true, but we want to talk about smaller windows. It's never. It may go up, it may go down. It's volatile, right? Stock market is never a stationary time series data. So ARIMA is not the best fit for that, and it will underperform in this case, and that will suggest that market is non-linear and is influenced by the complex factors. We do know that, but still we do want some baseline model, so we're gonna go with that anyway, because we are dealing with time series, and ARIMA is great with time series. Stationary time series, I should point that out, but we're still gonna go for that. The second baseline model, that is linear regression model. Okay, linear regression is not particularly a best fit again for this project. It's more generic model. It's not always used for time series data. It can be used, but it's not as best fit as ARIMA. But it's the traditional model. It's the first model everybody learns when they start with machine learning and data science. So and statistics in general. Linear regression is the first thing everybody learns. So that's why we're gonna consider using that. What linear regression does is basically it finds the best fitting line through the data that minimizes the error between the actual and predicted values. So visualize the graph with the two lines, dates on the x-axis and the values on the y-axis. One line suggests the actual stock market value, and the second line suggests the predicted values predicted by the model. And that will be a difference between those two data points, right? For example, on 12th of December 1980, my stock's actual value is 10, but my model predicted 12. So that will be a difference between those two. And linear regression is good at calculating those errors, the difference between those two. And that is basically called model loss in wider terms. When we'll be talking about deep learning, we will be talking about reducing that model loss close to zero. We do not want the loss to be zero. That would be overfitting. But yeah, we'll be talking about model loss later on. But let's talk about linear regression for now. We do know that we have engineered the new features and linear regression basically is gonna take into consideration all those features and will try to predict one of those based on the other features. For example, the target variable is log return. It will use all the other ones, learn the pattern over the data against log return, and it will try to predict the next outcome, next day's value of that log return. So again, linear regression has its limitations. It's not going to work well with the time series, it because it assumes the linear relationship between the features, which is not going to be the case here. It ignores the time dependency. Again, that's the crucial point. It does not take into consideration the time dependency of the features and the target variables. And in this case, we are dealing with non-stationary time series data. We do know that these two models are not going to be a good fit for this sort of data, but we do not want to assume in machine learning, data science, or AI project, you never want to assume anything. You want the data to tell us the story, right? And how will the data tell us the story? How will we know that this model performed well and this didn't perform well? Well, we do have some evaluation metrics for that. We will be using 3 of those. One is mean absolute error. It basically measures the absolute difference between the actual and prediction value. Absolute difference between those two. In the previous example, I took the actual value being 10 and the predictor value being 12. The absolute difference is 2 there. So that's the mean. If we take multiple data points and take the mean of those absolute, that's what mean absolute error is. It's useful in finance. It tells you it tells you how far the predictions are from the actual returns of the stock market. The second parameter that we're going to be calculating our model's performance with is MSE, mean squared error. So we do have actual errors, right? We do have actual differences. Square them up, square those values up, and take a mean of those. So that is particularly used in deep learning model. So in deep learning, minimizing those MSE, mean square error, is common because it makes that gradient smoother and easier to optimize. We will talk about that gradient optimization later on, but just so you know, that's how the mean squared errors are used essentially. The third matrix is R squared error. Basically, it's a coefficient of determination. It measures how well your model has explained the variance in the data. There are always variance in the data. For example, if R square value is 1, the model is perfect. It's predicting the values perfectly. If the R square value is 0, then it's not better than, let's say, calculating the mean of all the errors, right? For example, if I have 10 data points and the mean, I do know the mean value of those data points, and if I'm asked to predict the 11th data point, and if I say here it is, and it is the mean value of it, it's not better than that, right? And if the R square value is less than 0, that means it's worse than even predicting with its mean value. So it's especially tricky in finance because the return series are noisy and hard to explain. It's stock market data is really hard to generalize. So R2 score become tricky in this project as well. Overall, if I want to talk about in one word or one sentence, MSE, it helps penalizing the bad outliers for our model. It helps us to make the model tuning better. The MAE, it gives a clear idea of the average miss of the average loss of the model. And the R2 score basically tells us how much explanatory power our model has, right? How well the model predicted the values. And each one gives a different lens for us to look at the model and judge it based on those 3 different criteria to see how well it did. So anyway, we are going to be let's model those couple of models, ARIMA and linear regression. Then we'll create a function for calculating these three these three matrices. So I already have imported ARIMA here, and linear regression I have already imported the three mean, absolute error, mean square, and R2 score from scikit-learn as well. So let's go and first of all create a function to create those two baseline models. Just want to mention baseline models. Okay, let me take it a bit here so it's more visible. Anyway, first of all, ARIMA model, ARIMA baseline model, or baseline because we do know that model. We want to pass in the data y training. Y basically has the predictor, the variable that we are trying to predict, and y test. Okay, model equals to ARIMA. I have already imported it on the top. If you want to take a look, you can. ARIMA y train, order equals to 510. Again, if you remember what this 510 is, break it down. ARIMA, A, R, M, and A. So AR is 5. What AR is basically number of log observations that are used. The M is 1. The M is degree of differencing to make the data stationary, for example, removing the trends and stuff like that. And MA is 0, is the moving average term, how many past errors are considered. I don't want to consider any errors because I do not know if there are any errors in the past data, right? I want to tell the data. I want the data to tell me that stories, so I'm not going to pass anything for that, and I will simply return model.forecast. I want the model to predict the values. Steps equals to length of y test. I want to predict until there are values in y test. So that's the ARIMA baseline model. Let's do the same for linear regression. Linear regression baseline. Again, I'm gonna pass in x train, the feature set, x test, and y train. Model equals to linear regression. I have already imported it. Okay, x train. I'm gonna talk about x train, x test, y train in a later bit of part. We basically split the data, and we split the data in train and test. X train basically contains all the feature for training. X test contains the feature for evaluation. Y train contains the predictor, the value that we are trying to predict for training purposes, and y test contains the variable that we are trying to predict for testing purposes. So we do train the model and then we test it in the evaluation part. So these three matrices that we are going to be calculating, we first train the model and then we use the test data to evaluate those matrices. We feed in the data that that model has never seen before to see how well it performed on newer data. So that's what that train and test data is. So anyway, I want to fit this model with the training data, x train and y train, and I want to return the predictions of the model. Model dot predict x test. All right, so that's about that. Okay, I have a typo in return. Okay, now let's create the functions for evaluation of those models. I'm gonna be creating a function def evaluate model. I'm gonna be passing y true, y test or y true. Y true is more understandable, and y prediction, the predictor values that this model have returned, right? Remember, y test basically contains the actual values, and y prediction is the predicted value returned by the model. And now we will be calculating the three matrices based on these two values. So I'm just gonna print everything. Mean, absolute, error is simply have imported mean, absolute, error, and we'll pass this to y pred and y true. True means the actual value. Yeah, so that's mean absolute error. Same we will be doing mean squared error, and instead of mean absolute we will be using mean squared, and the same we will be doing R2 score, R squared, let's say R squared, that's score R2 underscore score. Yeah, that's about it. So that's our functions. We will not be modeling and testing the data in this video. We will just create those functions. In the next video, perhaps we'll do the splitting of the data, and we'll try to feed the data in these two models. And perhaps first we will try to make a deep learning model to compare that deep learning model with the performance of these models. So yeah, that's it for this video. I'll see you guys in the next one.